Okay, in this video, I'm going to be talking about transducers. What is a transducer? A transducer is a type of component that is like a translator. Okay, notice the trans, yeah? What it does is either it inputs non-electric signals like physical signals, physical quantities, and then outputs electric signals, or it inputs electric signals, outputs non-electric signals like physical quantities. So an example of a physical quantity, a non-electric signal, is like the lights. The brightness of my room right now is not an electric signal. Or sound, the vibrations in the air, that's not an electric signal. Or heat is not an electric signal. These are physical quantities. So the transducer, let's say, it inputs these physical quantities, then it outputs an electric signal, which will represent the level at which the physical quantity is at through electric signals, or vice versa. Vice versa, input electric signals, output non-electric signals. For example, a buzzer. I put in power, and its output is not an electric signal. Its output is a physical quantity. Its output is sound. So based off this already, we can actually split transducers into two different groups: input transducers and output transducers. And the only way they vary is what they produce and what they take in. So I'm going to talk about input transducers now, and then next I'm going to talk about output transducers. So let's start with the thermistor. Okay, the thermistor takes in temperature and outputs electrical signals. So the symbol for a thermistor looks like this. You will have this line, here, and then there'll be T and then a degree. But there are actually two types of thermistors. There is the NTC thermistor, which will be denoted by this minus, and there is the PTC thermistor. Nikki, what the hell does TC mean? What does PTC mean? What does NTC mean? NTC NTC means negative temperature coefficient, and PTC means positive temperature coefficient. How do they differ? These thermistors actually act like resistors, okay? And their resistance changes based on the temperature. For the NTC thermistor, its resistance plotted against the temperature would look something like this. So let's say this is resistance, let's say this is temperature. Give me a second. Sorry, this is what a textbook wants. As temperature increases for the NTC thermistor, the resistance decreases, and you would get something like this. So the colder it is, the more resistant the thermistor is. And the opposite can be said for the PTC thermistor. In the PTC thermistor, the colder it is, the less resistant it is. And we get something like this. So the hotter it is, the more resistant the thermistor is. So that's what you need to know. Oh, I forgot to mention at the start, you must know this. You must memorize this. Okay, this must be ingrained in between the cracks of your brain. Okay. Alright, let's move on to the next input transducer, which is the the LDR. Okay, the LDR stands for light dependent resistor, and I suppose you can guess its operation. It changes its resistance based on the light intensity around it, and this is the symbol. So we can actually plot a graph of its resistance and and the light intensity yeah. So how it goes is, if there's not a lot of light, it's actually really resistant. And as the light intensity increases, its resistance decreases. So yeah, that's very simple. That is the LDR. Okay, it's nothing else much to it. Okay, next input transducer is the microphone. Okay, the microphone. We have a microphone in our syllabus, and it looks like this. So what does the microphone do? Well, it notices the vibrations in the air. Okay, it notices the vibrations in the air, and it outputs an AC signal. Okay, that's all I'm going to talk about. I'm not going to go too in depth into it, because then we will have to go into things like inductors and magnetism. So I'm not going to talk about that, but I will say nothing. Let's move on. What other input transducers are there? I will now talk about a transducer that actually works both ways. I'm going to talk about the motor as an input transducer. The motor is famously known as a component that outputs physical turning, like a rotation. But actually, have you ever wondered, what if I take that spindle of the motor and turn it myself? What happens? Well, the motor will actually generate a current. What is going on? Sorry about that. The motor will actually take that turning, and will turn it into a current. That is all I'm going to go into. I'm not really going to talk about why it does that, because again, we have to go into inductors. So I'm just going to leave it at that. Just know that when you turn a motor, a current is generated. And I do believe that is all you need to know for input transducers. So let's move on to the next group of transducers, the output transducers. Since we ended with the motor, let's start with the motor, yeah? So very simply, when there's a current through the motor, electric signal, it will produce a turning force as its output, which is a physical quantity. That's pretty much it. However, one thing to note is that when you use a motor, let's say this is your motor, you must have a flyback diode. You must have a flyback diode. Okay? Why? Well, the motor is an inductor. Um, we don't learn what inductors are, but you can imagine it as a component that is like a capacitor. When you run current through an inductor, it charges up. But once you stop charging the inductor, it releases all its charge. The only difference between an inductor and a capacitor is that an inductor stores its electricity, or its charges rather, in magnetic fields. So why do you need the diode then? And why is it in reverse bias to the voltage? When you charge an inductor and stop charging it, it releases current in the opposite way it was charged. That's why the diode is reverse bias. Okay, why do you need a diode? When an inductor releases all its charge, it does so all at once, very quickly. That means the current is going to spike up to hundreds of amps. I'm not even joking. And that is going to destroy all your components if not properly protected. The diode eats all this current up. That's why the diode is there, to protect more vulnerable components. That's why the diode is there. Okay, and that's why when you're using a motor, you must have a flyback diode. This is known as a flyback diode. It is a normal diode, but its configuration gives it the name flyback diode. Okay, let's move on to the next output transducer. Let's move on to the buzzer. This is a buzzer, and when a current flows through it, it will give off sound, a physical quantity. And with this buzzer, you need to have a flyback diode as well, because it has a coil of wire inside. You must have a flyback diode. So that is the buzzer. Next is the loudspeaker. The loudspeaker is just a big. The loudspeaker is just a big buzzer. But I do believe the loudspeaker takes in AC signals. I think so. So yeah, I'm not gonna go into in too much depth of this because we don't even touch this at all. So yeah. Yeah, that's the buzzer. That's the sorry. That is the loudspeaker, and and I think that is it. There is one more uh output transducer, so to speak. It is the relay, which I go into far more depth in my relay video, but I suppose it could be counted as a transducer because when current flows through it, it produces a magnetic field, which is not an electric signal, which causes a physical change, again, not an electric signal. That's why the relay is also an output transducer, which you must know. And that is, those are transducers. You must know, you must memorize, you must know how they operate, you must know their symbols. Okay. And you must know, for those that have inductors, you must know to put a flyback diode. And that is it. Thank you for watching this video.